Now we'll be having a talk by Mr. M. Manoj, scientist from RCI. I'm happy to brief you about Mr. Manoj. Mr. Manoj working as scientist F in DRDO, India's premium defense R&D center, presently working at VLSI division of Directorate of Navigation and Embedded Computers, Research Center of Imarat, Hyderabad. He has done BE and ME from Osmania University, Hyderabad. He has architected, designed and developed system-on-chip ICs based on PowerPC and ARM processor platforms. He has various IP cores like Ethernet, DDR controller, avionics IPs like AR-INC 429 and AR-INC 664 and FPGA solutions, to name few to his credit. He has immense expertise and depth of languages like C, C++, Verilog, HDL, VHDL, System Verilog, System C and Perl, and IC or SoC design, and he has IC and SoC design at various process nodes like 90, 65, 45 and 25 nanometer technology, ASIC verification methodologies like VMM, OVM and UVM. He is honored with Agni DRDO Award for achieving self-reliance by developing indigenous ICs for missile systems. We are very happy to have you with us today, sir. A warm welcome to you.
Good morning, everyone. So I will explain about the semiconductor, from the semiconductor industry, the verification methodologies for system on chip. Why I have chosen this topic for this particular recent trends in semiconductor from Indian perspective is we have lot of jobs in verification environment, and these verification activity is as important as the design activity, and the number of jobs are very high. Second thing is even once we start verification, the effort which takes in the verification sector is almost equal to the design effort. Okay, so it is as good as design itself. Normally verification means there is a thinking that it is not as important as design, right? But even verification is very important, and it has got lot of importance, and it is very high paying jobs, one of the high paying jobs in the industry. So this is my agenda. It is a very small agenda: introduction, background of the system on chip, and SoC verification method. So here I will detailedly explain what all the different methods which we will be using for a SoC environment, and why we are using these kind of verification methods to achieve a defect-free chip, because the fabrication these days is very, very expensive. Almost a 28 nanometer SoC of size 10 by 10 mm square, 10 mm by 10 mm will cost around 12 crore. Okay, so if there is a small iteration required, then again you have to pay another 10 crore to 12 crore for the iteration. So it is a very expensive thing. So in order to have a defect-free chip, we have to do a lot of verification, and there are different methods which has to be adopted, and many training institutes are there, and these days we are getting very good companies to Hyderabad. All the MNCs are turning up here because of the China issue. So this is the time we have to, for in another 4 to 5 years, we should be able to grab the semiconductor industry so that we can be on par with China, especially from the electronics point of view. Okay, next I will explain about the sample design which I have executed. Then the trends from the foundry process nodes point of view, the device, the different growth factors which are driving the semiconductor industry, the packaging trends, and some of the AI related requirements and the performance factors which are required for various applications, followed by the capabilities in India, what we have now, and in the future, what we will be going to take the things. Okay, so system on chip. What is a system on chip? Right, right. So any system is it could be an embedded system. So system constitutes of a processor. To execute the code, we need a memory. HDL module. It can be in VHDL or Verilog, which will have the functionality of the respective digital logic. Okay, so this is a traditional embedded system with all the discrete modules, and if you try to understand this in a logical fashion, so these are the different functional modules it has. It has CPU, it has the memories. These are all the memory sections, the static RAM, the dynamic RAM, the communication peripherals, interrupts, and the codecs, the power supply. So, to make a system, we need, just now I was telling you about the digital logics like processor, memory, communication peripherals. These are the digital blocks. Apart from the digital blocks, we also require clocks like the PLLs. We require the memories, including of different technologies. We require the display. We also require the power supply, right? It could be different regulators, DC regulators, ACP, DC, and different kind of mixed signal chips also are required to make a complete embedded system. So these are the functional blocks. So to realize an SoC, what we do, we will first, I will explain from the digital point. Okay. So this is the power supply module. This power supply module, we cannot take it on the digital block. We have to remove it. A mid signal block, this can be kept, and the oscillators. So this will remove. Then these are the memories. So SRAM can be integrated onto the CMOS die. Coming to the DDR, it is a different fabrication technology. Then, right. So all the functionalities we will integrate now. All the functionality we will integrate onto a single die or FPGA. Okay, once we check it out, then these are the modules. We will integrate with the FPGA block and the memory, whichever is required. Okay. This is the statistical data which is taken up by taking up the failure rates of many chips, and which type of failure is significant and which type of failure creates a lot of impact. So 50% of the flaws are the functional flaws. Functional flaws. So almost 50%. What are the functional flaws? Functional flaws means if there is a design, the designer, whether he implements the design as per the specifications or not. If there is a gap or if there is a misunderstanding, then if a verification engineer do not able to catch that one, then that will go into the chip and results into a functional flaw. And other kind of things are the slow paths, the timing related things, the noise during the high frequency, if it is not taken care during the physical design, then the yield from the foundry point of view, the clocking, the race conditions, and the power domain, the power integrity if it is not taken care of, and some other things. So now we will concentrate about this 50%. I will today explain about the 50% of the functional flaws, how that can be avoided. So this is the place where now a lot of jobs are there, like the companies like Qualcomm, AMD, of course Xilinx is taken by AMD, and many semiconductor companies now which are coming to India, we have very good jobs here. Now coming to the verification methodology. So I think many of you have designed in VHD or Verilog some blocks, right? Yes? Right. Which language do you prefer, VHDL or Verilog? Why? Similar to, it is easy to program, like C. Why not VHDL? Okay, one is that ease of programming. Next, any other things? Or what is the disadvantage of Verilog when compared to VHDL? There is a big problem with Verilog. No. No, even Verilog doesn't support object-oriented. System Verilog supports object-oriented programming. Okay, Verilog is not a strict language. If we code in Verilog, we have to again check the Verilog code by using linting tools. Because the code quality, what a Verilog gives, is not up to 100%. But if we go with VHDL, it is 100% clean. Why? Because I will give you an example. Suppose if we have a signal of 32-bit, and if we are assigning a signal of 8-bit, let us think, by mistake, Verilog doesn't give an error. If you are assigning a 32-bit signal with a 8-bit signal, Verilog doesn't give an error, but VHDL will catch that. So if a designer by mistake does this one, and a verification engineer verifies only a 8-bit data, then once the chip comes up, then there will be a functional flaw. So in Verilog, we have to do an extra step that is called as linting, to have that language checks. Okay, so simulation is the basic verification method which is used by the designer, right? So a designer, whenever he designs a logic, he will first verify using simulation. Okay. Then what are the different types of verification? Do we need to follow all these verifications for SoC? For system on chip? Yes, we have to follow all these verification methodology. So we have lot of jobs. See, first I'll go with the semi-formal verification. Semi-formal verification is nothing but the verification with system Verilog, like the UVM methodologies, what we use. Then the formal method verification. So again, coming to a different classes, if we just see, this formal verification, anybody heard of this formal verification? I think many people might have heard, right? So this is a static verification, means mathematically it will compute the correctness of the code. And hardware accelerated simulation. This is also coming up with like different tools are coming up with accelerated verification, emulation. Emulation tools are there which will emulate the complete design into a different hardware. And if you see the simulation versus emulation and simulation versus prototyping, there are different speeds. Like if you want to simulate, if you want to run a suppose 1 millisecond time frame of a design, suppose SOC design, if you want to run in verification and in the simulation kind of environment, it will take around 1 second of real time, roughly. 1 millisecond of the run will take around 1 second, almost 1000 times it is delayed. Whereas FPGA, it is faster and emulation is still faster. Okay. Okay. Now this is the regular flow. Okay. First we'll get the specifications. Once we get the specifications, then we do hardware software partitioning, which logics can be into the hardware, which can be into the software. Based on that, we will develop the IPs and we will do the verification, then the integration. Here the SOC is formed here. All the IPs are integrated and the logically SOC is ready at this stage, IP level stage. Then we will do a simulation. Once we do a simulation, we will go for a prototype. So this prototype we use FPGAs because FPGAs are like almost some 20 to 30% of the final product, because we can run for longer times. The design which takes suppose 10 days to run on a simulation environment, it will take some 10 minutes in an FPGA design. So that kind of difference we have. So we go for the FPGA prototype, then finally the development part. These are the same, the sequential and parallel. Okay. This is called as electronic system level design, ESL. What we do, suppose, see, we are verifying based on the specifications which are given to us. So based on the specifications, a designer will design and a verification engineer will verify, right? But how do we know the correctness of the specification? Whether the specification is right or wrong. So once a specification means once a rough architecture, okay. So how do we verify the architecture? Suppose if we have a mobile phone kind of application. So what is the input data rate, what is the bandwidth, and what all the real-time latencies we can accept. All the things has to be considered from the application point of view in order to make an architecture, right? All the frequencies, the buses what we choose, the bus width, okay. So all this has to be selected based on the specification. And how do we verify the architecture? So these are the first stage of the design, architecture, right? So architecture can be verified using ESL, electronic system level languages. So here we use System C. System C is a language which is used to verify an architecture. So here what we do, using System C, we will model the complete system. We will model, this is the one of our chips we made with PowerPC SoC. So we have designed this complete architecture using System C. This is the PowerPC 440 processor. And to make this complete system, it will take less than a week. So suppose if you want to make an architecture of a mobile phone and check the real-time scenario, like we use MATLAB for the algorithms, right? So in the same way for the SOC, we use the system level, electronic system level languages. So we can model the complete system architecture wise, and we can see all the parameters of a design, whether they are satisfied, whether the ranges what the parameter are supposed to do, whether these are correct or not, everything we can verify based on this system level verification. So once the architecture is verified, architecture is proper, okay, then we can also port operating system. Okay, like Android, we can put operating system on the device and check whether everything is okay or not. So once the architecture is clear, architecture is cleared by the architect, then we'll go ahead with the module verification, block by block verification. Okay, so this verification, module based verification, these are the different stages of verification. First we'll go with the block level verification. Like a processor verification separate, a communicating IP will be verified separately, a memory controller will be verified separately. So here we will go for 100% coverage. Coverage is one of the metrics which is used to state that design is verified to the 100% or not. So that coverage matrix is very important. And the cluster level verification. If you have a bigger system, so there could be a high speed cluster, slow speed cluster, imaging cluster, different kinds of, some Wi-Fi cluster. So cluster level design, because the modular design will come up once the complexity increases. Then the full chip, integrated level chip analysis. Okay. So this is that coverage driven verification, which I was explaining about. This is important. Randomization is to create a random vector in order to, suppose if we have a 32-bit address bus, how many vectors we require to verify that address? 2 power 32, but we cannot verify those many, right? So we will use this randomization. So there is some concept called as constraint randomization, where we can give the boundaries, what are different sectors, and give how many number of vectors we want to generate. That is called as randomization. Okay. And for all this, we use a verification language, System Verilog. Previously, for architecture, which language we use? System C. Yeah, here we use System Verilog. So this is OOPS based language, System Verilog. Okay. And coming to the coverage driven. Now this is the design which is given to a verification engineer. So verification engineer's job is what? To verify, yes, verify the correctness of the design, right? So verification engineer has to catch the bugs. Then only his job is, he has properly done his job, right? He has to catch the bugs in the design. So he has to verify this design from the point of bugs. He has to catch the bugs. So first thing is, as somebody was telling, the functionality. So based on the features, whether all the features what are given, whether the designer has understood all the features, what is expected to be implemented, or any design issues are there, everything a verification engineer has to verify. So as per the coverage driven verification methodology, first a driver will be there. So this driver will generate all the vectors which are required. So suppose if this is a subsystem, a UART communication system, this particular IP has a UART communication this and others is this is the bus communication. This is on-chip peripheral bus. This is an SoC, system on chip. It is also the backbone of a system on chip is a bus architecture, bus. If it is ARM, it is AMBA architecture, right? If it is power PC, that is called as core connect architecture. So as part of the core connect, we have a slow speed bus called OPB. So processor will be connected here in the final SOC. Processor will access this UART for the communication. Now we have to verify this UART. How do we verify? So we need to make the test bench in system Verilog in UVM methodology. So first it has a driver, then this is a receive part of the UART. We will generate the random sequence and check whether complete spectrum of the data is checked or not, and then the input output. So this side is the processor bus implemented here. This side is the line side, whether the data what we are giving and the data what is captured. So here is the serial data, here is the parallel data, right? So whether this particular thing is okay or not, there will be a checker here. It will check the serial data will be coming here, converted to parallel data. Same parallel data will come here. Both are compared for the correctness. Okay, right. So independent checking will be carried out, and the coverage. So what part of the design is covered? There are different coverage metrics like code coverage, functional coverage, right? Again, in functional coverage we have different bins. So what all the parameters we want to cover functionally, we can implement that. Okay, this is called as coverage driven verification. This is the primary and the most significant part of a verification. As I was explaining previously, block level design should be 100% covered. Right? Okay. So this is one of the chips I was explaining right previously, the power PC. It has got different peripherals, the memory controllers, memories, high speed communication like PCIX, PCIe, USB communication, and different slow speed connectivity. These are our avionics communication buses, Ethernet, and this is the typical verification environment based on UVM. So how many of you know what is UVM? Yeah, universal verification methodology. So previously, initially it was based on very native Verilog test benches. Then came Vera from Synopsys and E from Cadence, E language from Cadence and Vera from Synopsys. So these are object-oriented languages which were used to verify, because in a system, in a SOC level verification, suppose if we take a mobile kind of a system on chip, mobile phone system on chip from Qualcomm, for each run, a verification run, around 5 GB data will be dumped out into the RAM. And suppose if you want to verify some 10 such test cases parallelly, then almost 50 GB of RAM is required. 50 GB of RAM is required. Normally we use, these days okay, we are getting 64 GB, 128 GB also, but it has to execute other tasks also, right? So system will be very, very slow. So that is the problem. So then came up with this kind of UVM verification methodology. This is based on OOPS. What is the main advantage of OOPS? Object oriented, correct? Anyway, we know it is based on the 4 pillars like polymorphism, inheritance, all those things. And what is the main advantage of OOPS? OOPS, right? The concepts of OOPS will be implemented using classes, the structures, right? Right. That is the structure. OOPS is a concept built on this structure, and why this kind of OOPS is required? Sorry? Write one, run anywhere. Okay, so you are telling it is a tool independent kind of thing. Reusability, that is a very good point. Yes, reusability. Next. Yeah, reusability, yes. Reusability is one of the very important factors, because once a small design, once it is made, it can be a little modified because it is an object, right? So it can be called into the classes and it can be modified. Reusability is one part. Yeah, inheritance is the same reusability, right? So you inherit that properties and make the thing. Once you make an object, you will create, you will store it in a library. Here, what we call as a factory. Once you register to the factory, you can reuse anywhere. So almost 50% impact will come with the reusability. Second important thing is the memory, which I am telling, right? So if it is a Verilog, if we have a different kind of modules, then each module will be implemented again using, internally it will be C, right? Again internally a source code will be there. So suppose if we make a SOC kind of this kind of big verification model for the complete system on chip, then the data verification environment will run out to around some 40 GB, 50 GB. Whereas if we use OOPS, the objects are created runtime and destroyed runtime, correct, right? So the 50 GB might turn down to some 10 GB only. So the memory utility, dynamic memory allocation, so that is the second part, right? So these two are the major factors of OOPS which are taken care in this UVM verification methodology. And this is a presently OVM 3 what we are using now. Previously OVM 2 was there, 1, and before this there was an OVM, open verification methodology. Okay, right. So once if we learn this UVM, we can run this UVM based verification methodology using anyway all of our tools, Synopsys, Cadence, and Mentor also. Questa is mostly I should not tell, but crack tools will be available, right, Questa. So especially the students, they can learn UVM with Questa. Directly ready-made environments will be available in the internet that can be taken and can run on this UVM. So this complete environment is made using system Verilog, and it should be an automated environment. Automated environment means with a single click complete execution should happen. So system on chip, what are the different activities in the verification? First is the C code, right, because it has to run on the processor. So C code should be compiled. So if we take a test case, a C code should be there, C code should be compiled. There could be different inputs, C code should be compiled. And second thing, once we generate a hex file, bin and hex file, that has to be backdoor loaded into the flash and respective memories, the code. So that is the first step, the C code. Why I am telling all these things? It is background is Perl. Okay, Perl will be used to automate an verification process. So what is the verification process is? First is the C language that has to be compiled, loaded into the respective memories. Then second step is it has to compile all the design, complete design. Third, it has to compile complete verification environment which is built in UVM. Once compilation is ready, then the test bench, again the test bench will come into picture. It has to give a reset, the clocks, and then the process starts executing from the, it will read from the respective code memory and the data memory, it will execute and do the respective communication tasks, right? So all these things, there could be around 20-30 different tasks which we have to run. Instead of that, to automate it, we will use Perl. Okay, Perl also is a very simple language, so that can be used to automate the verification environment. So system Verilog is required, Perl is required for a verification engineer. So multi-language plugins, yes, we have seen that debugging coverage map. So once everything is done for each test case, the coverage will be cumulatively taken and the complete coverage of a SOC will be done. Because see, already I have explained the block level coverage will be done 100%. So once we do the block level coverage, then next thing is SOC is the integration only, right? It's a system integration or IP level integration. So once the IP level integration is there, then we need to check only the integration. So what we do is a toggle coverage of all the interfaces, whether all the buses are toggled or not, write, read, address, data, okay, different kinds of access, whether everything is covered or not. We will do the toggle coverage. Once we do coverage mapping, then we will go for the bug breakup. So once a verification engineer he runs, he will catch the bugs and make it into that environment. Okay, and that is the logic level design. And then it goes to the, after the logic level design, then what we will do, we'll synthesize, right? So again in semiconductor field, synthesis is one of revolution, one of the revolution, what I can say, okay, it is a magic thing, okay, synthesis. Only because of synthesizing this complete VLSI has come into, only because of synthesis this complete VLSI has flourished in this way. Because previously the complete electronic design used to do by hand, right, with the schematics, the transistor based design. Once the synthesis came into picture, then tools only are synthesizing the top level or higher level behavioral language into the lower level gate level language, right. So what they say is, suppose if the synthesis kind of tool comes into aviation sector, suppose it has come into automated synthesis, came into electronics, right, digital side. Suppose the same kind of thing comes into the aviation field, this kind of innovation. Then from Paris to New York, the travel will be in 2 minutes in 2 cents. Means that kind of drastic changes will come. So what I mean to say is the importance of synthesis. Synthesis is the major tool which has paved the technological growth in the electronics. So once a design is synthesized, the synthesis design will place here. Again we will run the same environment to check whether the synthesis is proper or not. After that, we will go for the layout, place and route, and post place and route also the same netlist will be taken, timing netlist, will plug in the same UVM environment, run the test. Okay. So with this we will clear the logic level design. Okay. So this is the UVM verification environment. It is based on the OOPS, again the same, the agents will be there here. What we have to remember is the agent. Agent is the main module. In this agent block, we have the respective internal classes. Each is an object, okay. So we will take that methods in that and we will integrate. This I will go faster. Okay, code verification. Okay, this is what I was explaining previously. The same C code compiled and the ELF or hex file will be generated, the first step. Then the bit stream. So this is the FPGA point of view, and the place and route netlist will be generated. For the ASIC, we go for the GDS, right? We go for the foundry, and we'll check. Okay, this is just the flow. We all know. Hardware accelerated simulation. Okay. So it is faster, but the setup time is more. Emulation, there are different kinds of emulators from Cadence, Mentor. From Cadence it is Palladium, from Mentor it is one tool is there, Mentor. Okay, right. So it is 1000 times faster than the simulation if you use the emulation. Okay. The SOC kind of design, once we make design using the basic EDA tools, we go with the emulator then. So complete design will be mapped onto the emulator. Emulator can be FPGA based or it can be a ASIC based. So the mentor thing I was telling you, it is called as Veloce. Cadence is from emulator of Cadence is Palladium, and mentors it is Veloce. So for system level simulation, so for like the mobile SOC, if we want to verify with emulation, we can port the operating. Previously we have seen the architecture level, right? ESL, same kind of verification can be done using the emulation. So then the ASIC prototyping. So here we will use FPGAs. So this is like near real time. FPGA prototyping of an ASIC is, ASIC prototyping using FPGA is near real time, almost like 100%, so 10x slower, that's all. Okay. So this is one of the FPGA prototyping which we have developed at our place with 4 FPGAs talking together for the same kind of SOC. We have ported complete SOC into this one and verified. It has got some 24 daughter cards for all the things, and we integrated all. We have different connectors here, 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 here. All the daughter boards will connect and will verify the design. To make a mobile chip, like a Qualcomm kind of chip, what could be the cost from start to end? Suppose if we take octa-core kind of a mobile, so Qualcomm any series if we take, roughly it might take around 300 to 400 crore to make a complete chip. The design, verification, the IP cores constitute the major cost. 300 to 400 crore for the making of a mobile chip. Okay. So you have to thoroughly verify. Okay, SOC. Okay, this I have. I'll anyway share the slides. So this you can go through. This is the architecture what we have done. Okay. So once we run that one, we will get the different bugs. We can see finally the bug should be 0. This is the flow, what we go ahead for the ASIC. These are the standard things anyway. So this is the major challenge of an ASIC design. We have VHDL blocks, Verilog blocks, System C blocks, System Verilog blocks, Perl, multiple languages, multiple tools. Of course, many people are required. Okay, and coming to the trends. I'll take another 5 minutes for the to explain the trends. So these are TSMC process. So presently we are doing 1 nanometer also, 1 nanometer, 2 nanometer, and why I kept is 3 nanometer is under production. It is stable now, 3 nanometer. And before 3 nanometer we have 16 nanometer which is stabilized and 28 nanometer. Okay, these are the stable technologies. Okay, and coming to from the major foundries, different technologies are there. Okay, and from industry segment point of view, okay, defense, military, what amount, what is the amount which is contributing to the market, and what all the different kinds of process technologies which are being used now, from the 18, 10, 20 nanometer to the 65 nanometer, what all things. What is the share of that market share for different process technologies presently? Okay, and different process nodes, where do we use more beneficial things, based on the speed, the cost, okay, and different device models. Previously it was a planar technology, right? Planar, then it came to the FinFET, then it came to the gate all around FET, and in future that CFET, again complementary FET is coming up. For lesser than 1 nanometer, we'll go for this CFET kind of things. So now we talk about angstrom. Now the nanometer era is over, we talk about angstrom now. Okay, so that CFET which I was telling, right? Then slowly we are migrating towards the carbon nanotubes. That will be in the future, maybe another 2032 I was telling, right? Then that time all carbon nanotube based devices will be there. Okay, the different growth factors are driven by the consumer electronics, automotive, telecommunication. These are the major technology driven markets. This is affecting the complete technology spectrum, and from the mass to get these kind of parameters which are required, we have to go with the higher process technologies, the manufacturing, and the different technologies which are revolutionizing the lifestyle of human beings. Expansion, okay. In India now this is coming up, the OSM, outsourced semiconductor manufacturing. OSAT we are talking about, right? The OSAT. Okay, OSAT is outsourced semiconductor assembly and testing. All the packaging, the validation, except foundry, the latest foundry, we have everything in India now. Suppose, okay, these are the trends, okay, I'll explain that. So trends, again, those are the growth driving factors, and the trends in the process technologies, 7 nanometer and below are the stable technologies which are coming up, which already came, and these are stable technology I'm talking about. Test chips are being done at 3 nanometer, that is also getting proper stabilization. Stabilization is the word which is used with respect to the yield, okay? And the rise of the AI chips, 5G, 6G, automotive, Internet of Things, cyber security. Apart from these things, there are other things also like medical, space, okay. This is, here you can see different kinds of the technologies which are used for different kinds of sectors, processing, memory, the connectivity, power. Power still we are into 130 nanometer only. Power modules like the regulators, sensors, okay. And coming to the packaging trends also, we have different kinds of packaging, okay. Bonding wire, die attach, different kinds of packaging technologies. And again the scope in India, presently we have a fab from SCL Chandigarh, that is 180 nanometer only we have in India. This is there from past many years, driven by ISRO. It is in Chandigarh. So with 180 nanometer also we can do many chips which are required, like mixed signal chips, ADCs, DACs, which are required for our application. Always we need not go for the latest technology, correct? Only latest technology we go wherever we require higher speeds and huge volume. Then only we can go for the latest technologies based on cost. Then again, now we are getting 65 nanometer technology from Tower, Israel. Mostly by next year, that should be next to next year, it will be operational. Again, in the same SCL facility, we are getting this Tower Semiconductor foundry. Because I'm talking from India government point of view. Okay. Anyway, we know that private industry, the Tatas are coming, okay, and others also are there. So that skilled manpower is very much required, and a lot of opportunities are there, because we are the country which are alternate to China now. So in this complete IC manufacturing thing, this is a complete value chain, this complete supply chain or the development chain, where only this Foundry is what is lagging in India, except that we have everything here. Again the same, only the materials also we don't have. This is the OSAT which I was telling about. The semiconductor mission which is being taken up now, almost 50% of the funding is given for the OSAT. The packaging, okay, these things. And again coming to the AI, so what all the different performance requirements. For digital, what all the performance metrics we use? We use DMIPS, right, for the digital part, the processing. DMIPS. For the regular scalar processing, we use DMIPS. DMIPS is the, what is DMIPS? Okay, how do we quantify a chip from performance point of view? MIPS, millions of instructions per second, right? What is our performance? DMIPS is dystron. Dystron is a standard routines which are available. Once we run on a system, we will know the performance of that particular system. We can quantify a system based on DMIPS. Okay? So, from if we talk about performance, the processor performance will be counted in DMIPS, the scalar processor. If we talk about a vector processor or a DSP signal processor, it will be in flops, right? We use lot of MAC, FFTs, right? What is flop? Floating point operations per second, okay? Floating point operation per second. That is for the signal processing or vector processing. So, scalar processing is DMIPS, vector processing or signal processing we use flops or gigaflops, and for AI, now we use TOPS. It is tera operations per second, okay? And if we want to do different kind of operations or tasks, what kind of TOPS are required, okay? So, presently we are designing a chip, a multiprocessor SoC, which has 40 TOPS for our internal application. So, 40 TOPS. So, you can see the different kinds of applications and what kind of performance are required. So, once we see any hardware, we have to see what is the TOPS once we look for the AI kind of applications. Okay? This is very important, the TOPS. Okay? Similarly, and what kind of MAC, the background MACs which are required to generate that kind of TOPS. So, mostly we use 8-bit MAC only for the applications. Okay, you can see. Okay, and the different manufacturing things which are coming up. Again, in Telangana now we have only a few things which are kept, but now Hyderabad is next to Bangalore. So, in future we should be like China. So, we will be getting lot of fabrication facilities and design and packaging houses. Thank you. If anybody has any doubts or queries, you can ask me.
Engineer needs to bother about the technology.
He need not have to bother, but he should know about the technology trends. Why? Because a verification engineer, if he knows about the timings which are going down the line, like the post synthesis, we have zero wire load models, we don't have time. But once we go for the post placement, post CTS, post routing, then we have the timing related things. Then if we know the process technologies, then what kind of verification we have to adapt, that will be helpful.
What kind of verification means?
The timing verifications.
Okay.
How there will be some X tracing.
So whether this using UVM methodology, is there any thing to do with the timing?
Yes.
The guy who deals with UVM.
Yes, yes. So once we run a UVM based framework, output again will be a waveform only, right? Yes. So waveform could be a digital data or lot of X propagations will be happening. Once we go below the logic level, once we go below the HDL, that is the synthesis onwards, we will be getting lot of X propagation. Yes, yes. because of the violation of setup hold, these X timing violations, we will
Yes.
get that X propagation. So in order to understand this X propagation in UVM also, we need to know these things, timings.
Thank you, sir.
Because of the violation of setup hold.
Thank you. So, UVM guy, they focus primarily on, writing the test cases, verification cases, all possible. So, are they going to take any timing library also to include with that verification environment?
Good question, but they don't take it. Timing libraries will not be taken by verification. Only timing libraries will be taken by the designer only.
Yes.
During synthesis
Yes.
and physical design.
Okay.
And a verification engineer will be working on the boundary, right?
Yes.
Roughly like a black box.
Yes.
Initially.
Yes.
He is not worried about a gray level of seeing or even a white level of seeing. First he will worry about only the black box.
Yes.
Their input to output timing only he is worried, verification engineer.
Yes. So when he's not taking those libraries, then how is that it is important for him to know that technology?
That libraries are not concerned for verification engineer, but he need to know what all the timing. Suppose if we go from 65 nanometer to 25 nanometer, what kind of timing improvement it comes.
Okay, got it.
So
Yeah.
again, so because from 65 nanometer to 40 nanometer if you go, or 65 to 28 if you go, voltage levels change from 1.8 volt to 1 volt.
Yes.
Once we go below that, again we will come to the 0.9 volt.
Yes.
So once the voltage level is coming down, the timing will increase.
Yeah, got
Right.
it.
So
Thank you.
that kind of setup hold violations, here a verification engineer should able to tell the designer where is the setup hold time and violations are coming and why.
Yeah, thank you.
Morning, sir. As an MTech student, what does the industry expect from our students based on verification rule?
If you can independently make a UVM based verification environment, okay, then that is sufficient for any company to take you.
UV is enough,
UVM
sir.
based verification
They
environment.
tell us to learn system Verilog and protocols
Right,
and all.
right. So UVM based verification environment means background is system Verilog. There is a site called testbench.in.
Okay.
So if you see the testbench.in, you will have the complete description and sample codes with explanation.
Okay.
The same code you can use and directly you can implement in Questa
Okay, sir. Thank you, sir.
and you can run that.